Okay, so now I'm going to discuss the normal equations, which are the equations that we're going to solve in order to find a solution that is closest to a solution in the sense of least squares. And the term normal, think of that as meaning orthogonal or perpendicular. And as far as how that comes into play, as I said, in class, I'll go over the theory some more. But normal here means perpendicular. Okay. So the normal equations are, so let me first write to solve, let's say to find a solution in the sense of least squares. To our linear system of the form ax equals b, we solve the normal equations, which are A transpose A x equals A transpose b. These are the normal equations. Okay, so I mean this concept is pretty easy to apply. We have our example from the previous slide that where we have our x1 plus x2 equals 2, x1 minus x2 equals 1, x1 plus x2 equals 3. Of course, we can write this in matrix vector notation, so I'll do that. So in matrix vector notation we have a 3 by 2 matrix with 1, 1, 1 as the first column, 1 minus 1, 1 as the second column, okay, times our unknown vector x, and this is going to equal our vector b, in this case is 2, 1, 3, okay. And so this is our system that's of the form ax equals b, and does not have a solution. However, we can solve the normal equations to find our least square solution. So our A transpose is, of course, we take our column of A and write it as a row of A transpose. And so this is our A transpose. And if we multiply A transpose times A, I'm not going to write out the details here. I'll ask you to check that. If we do A transpose A, we get a 2 by 2 matrix that looks like 3, 1, 1, 3. Notice that it's symmetric, not just a coincidence. If we compute A transpose B, we get the vector 6, 4. Okay? And so now we solve this 2 by 2 linear system for what I'll call x hat. And so if we solve this linear system, and so writing it out, we have this 2 by 2 matrix times a vector x1, x2 equals the vector 6, 4. And if we solve for what I'll call x hat, we get the solution 7/4, 3/4. And so now, if we just check on the product of our matrix A times this solution, and so just to back up for a moment, let's just note that x hat is called the least square solution. Okay. And let's check to see what A, our matrix A times x hat gives us. So A is our matrix 1, 1, 1 in the first column, 1 minus 1, 1 in the second column, times this vector 7/4, 3/4, and this computation leads to the vector 2.51, 2.5. And clearly this does not equal what we would like it ideally to equal, which is 213. And we knew that we weren't going to get a solution, so this of course has to be true. Alright, so now having computed AX hat, we're going to define some things so that we can maybe establish a measure of success. And so I'm going to define the residual vector. So the residual vector, which we label as R, is going to equal B minus A X hat. Okay. And so in this case, so this is a general definition of the residual vector, but in this example, you can see from if we subtract AX hat and R, our residual vector is minus 0.5, 0, and 0.5. And using the 2 norm, we can actually compute the 2 norm and so the 2 norm of this residual vector is just a square root of a sum of squares. And so generally speaking, we'll just do it specifically for this problem. So the 2 norm is a sum of squares. So if we square if we do square root of minus a half, we get a fourth. Of course, squaring 0 is 0. We square another 1/2, which is a fourth. So underneath the square root, we add 1/4 and 1/4 to get a half. So this equals the square root of a half. Or if we rationalize this, this is root 2 over 2, okay, or roughly 0.707. There's another quantity that we can define in trying to understand or get a measure of a success, which is the root mean square. So now I'm going to define the root mean squared error. And so this is going to be abbreviated RMSE. And so our RMSE is going to equal the square root of SE divided by M, where SE is basically equal to the square of the 2 norm of the residual. Okay, so it's basically a sum of squares. It's R1 squared plus dot 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 plus R sub M squared. Okay. And M is the number of data points. And so for this problem in particular, it turns out that our root mean squared error computes to be basically, we would be taking that sum of squares that we had underneath our square root for our computation of the 2 norm of R and divide that by 3. So if we take our 1/2 and divide by 3, put that in the square root, you see that the root mean squared error is the square root of 1 over 6, and this is approximately equal to 0.408.